Tonight, we begin with a thought that feels simple, almost harmless, yet quietly destabilizing. Time may not be flowing at all. The steady forward motion you feel, the sense that moments pass from future to present to past, may not exist in the universe itself. It may exist only in how your mind experiences reality. Physics allows this possibility, and once you see it clearly, time never feels the same again. Everyday life trains us to trust time completely. Clocks tick, calendars turn. Events happen in sequence. Morning becomes afternoon. Childhood becomes adulthood. Cause precedes effect. Everything feels anchored to a moving present moment that slides forward through an ever-vanishing future. This experience is so universal that questioning it feels almost absurd. And yet, when physicists write down the deepest equations describing reality, something strange appears. Time does not move in those equations. It does not flow. It does not point forward. It simply exists as a dimension, much like space. This isn't a philosophical trick. It's a mathematical fact. In classical mechanics, quantum mechanics, and even general relativity, the fundamental equations don't require a flowing present. They work equally well whether time moves forward, backward, or not at all. The laws themselves are indifferent to direction. They describe relationships between events, not a story unfolding. This creates a tension between experience and physics. On one side, your inner life is structured entirely around the passage of time. On the other, the universe appears perfectly content without it. So where does the feeling of time come from? To approach this question, we need to slow down and examine what time actually is in physics, not as we feel it, but as it appears in our best theories. We begin with something familiar: space. Space feels obvious. You can move left or right, up or down, forward or backward. You can measure distances. You can point to locations. Time feels similar. You talk about earlier and later, past and future. But in physics, time behaves differently. You can move freely through space, but you cannot move freely through time. You remember the past, not the future. Effects follow causes. This asymmetry feels fundamental, but physics doesn't enforce it. Einstein's theory of relativity treats time as part of a four-dimensional structure called space-time. In this picture, time is just another coordinate, not special, not flowing. Events are points in space-time, each with a position and a time. The universe becomes a four-dimensional structure where all events exist together, laid out like a completed landscape. This view is called the block universe. In the block universe, the past still exists. The future already exists. Your birth, you're hearing this sentence, and events billions of years from now all coexist within the same space-time structure. Nothing is coming into existence. Nothing is disappearing. There is no cosmic now sweeping forward. There is only the block. This idea is unsettling because it contradicts the deepest intuition we have about reality. It suggests that the passage of time is not a feature of the universe. It is a feature of consciousness. But before we dismiss this as abstraction, consider something important. The block universe is not speculative philosophy. It's the natural interpretation of relativity. And relativity has been confirmed countless times. Time dilation, length contraction, gravitational time slowing, all observed, all real, and all consistent with a static space-time where time does not flow. There is no experiment that detects the motion of time itself. Clocks don't measure time flowing, they measure change. A clock is a physical system undergoing regular motion. A pendulum swings, an atom vibrates, a quartz crystal oscillates. We interpret these changes as time, but time itself is never observed. Only change is. This distinction matters. If nothing changed, time would be undetectable. A universe frozen completely wouldn't feel timeless from the inside, because there would be no inside experience at all. Experience itself requires change. So perhaps time is not fundamental. Perhaps it emerges from change rather than causes it. This idea is radical, but it has deep roots. Even Isaac Newton, who treated time as absolute and universal, admitted that time itself could not be directly measured. He distinguished between true time and relative time. Relative time was what clocks measured. True time was an abstract concept. Modern physics goes further. It suggests there may be no true time at all. In quantum mechanics, time plays a strange role. It's not an operator like position or momentum. You can't measure time the same way you measure distance. Time enters equations as an external parameter, something assumed rather than derived. This asymmetry hints that time might not belong in the same category as physical quantities. When physicists attempt to combine quantum mechanics with general relativity, time becomes even more problematic. In quantum gravity equations, time often disappears entirely. The fundamental equations describe relationships between configurations, not evolution in time. This leads to what is called the problem of time. At the deepest level, the universe may not evolve. It may simply be. If that's true, then the question becomes unavoidable. Why do we experience time so vividly? Why does now feel special? Why does the future feel open and the past fixed? To answer this, we must shift from physics to information and thermodynamics. One key concept is entropy. Entropy measures the number of ways a system can be arranged while appearing the same at a macroscopic level. Low entropy means order. High entropy means disorder. The second law of thermodynamics states that entropy tends to increase. This creates an arrow of time. But here's the crucial insight. The arrow of time comes from entropy, not from time itself. The laws of physics allow entropy to increase or decrease. They don't prefer a direction. The universe began in a very low entropy state. From that special beginning, entropy has been increasing. This gives rise to the direction we experience as time. Memory works only because entropy increases. You can remember the past because physical records exist. Photographs, brain states, fossils, light traveling from distant stars. All of these are low entropy structures that persist. The future has no records because it has not yet increased entropy in those ways. This makes the present feel like a boundary, but it's a boundary created by information flow, not by physics enforcing a moving now. Your brain constructs time from memory and anticipation. Consciousness itself may be a process that orders experiences sequentially, creating the sensation of flow. Without memory, there is no past. Without prediction, there is no future. The present moment is where memory and anticipation meet. This doesn't mean time is an illusion in the sense of being fake. It means time is emergent. Just as temperature emerges from molecular motion, but doesn't exist for a single molecule, Time may emerge from complex systems interacting, but not exist at the fundamental level. This reframing changes everything. It means that the universe isn't waiting for the future to happen. The future is already part of the structure. What we call becoming is our traversal of information states. This idea has profound implications. It suggests that free will, causality, and meaning need not disappear, but they must be understood differently. Choices exist as patterns within spacetime. Causes and effects exist as relationships between events. Meaning exists because conscious systems experience ordered sequences. The universe doesn't need time to flow for life to feel alive. As we continue this series, we'll explore how black holes distort time, how quantum mechanics challenges temporal order, how cosmology treats the beginning of time, and why some physicists believe time itself may dissolve at the smallest scales. But for now, let this idea settle gently. Time may not be a river carrying you forward. It may be a landscape through which your awareness moves, and that difference changes how you see everything. Thank you for watching. Don't forget to like and subscribe for more deep dives into the nature of reality. Have you ever felt like time is slipping through your fingers? Like the present moment is a fleeting thing, constantly vanishing into the past? Every event that has ever happened or ever will happen has a specific location in this fabric. Think of it like a giant loaf of bread. Every slice is a moment in time, but the whole loaf, the entire history of the universe, exists all at once. This might sound like abstract philosophy, but it's driven by hard physics, specifically something called the relativity of simultaneity. But Einstein proved this is not true. Imagine two people moving relative to each other. The GPS in your phone has to constantly correct for these time dilation effects to give you an accurate location. Time itself is relative. It depends on your speed and the strength of gravity around you. If there were one single objective now for the entire universe, everyone would have to agree on it. But they don't. The unavoidable conclusion: there is no universal present moment. This is where our everyday intuition really breaks down. It means that the division of time into past, present, and future isn't a fundamental feature of the universe. It's a feature of us, the observers. Each of us is experiencing our own unique slice of space-time. Your deliberations, your decisions, and your actions are the very events that help form the structure of the universe. Your brain is constantly stitching these snapshots together, creating the seamless feeling of a present that's always moving forward. You deliberate, you weigh options, and then you act. Why does time feel so one-directional? Why does it seem to march relentlessly from past to future? Why can we remember yesterday but not tomorrow? If the basic laws of physics don't care about the direction of time, where does this powerful feeling come from? The answer, it turns out, isn't found in time itself, but in a concept called entropy. Entropy is one of the most misunderstood ideas in science. People often call it disorder, but that's just a rough metaphor. A better way to think about it is this. Entropy measures how many different ways you can arrange the tiny parts of a system while keeping its overall appearance the same. For example, a neat stack of papers on your desk has low entropy. There are only a few ways to arrange them to look neat. But if those papers are scattered all over the desk, that's high entropy. There are countless ways for them to be scattered and still look messy. Now, the second law of thermodynamics says that in a closed system, entropy tends to increase. This isn't a strict rule about time. It's a statistical law of averages. Systems naturally move from unlikely states to likely ones, simply because there are vastly more ways to be in a likely state. This statistical tendency is what creates what we experience as the arrow of time. Here's where it gets really interesting. The laws that govern how individual atoms move don't have a preference for forward or backward in time. If you recorded a video of atoms bouncing off each other and played it in reverse, it would still look perfectly normal, according to the laws of physics. At the microscopic level, reality is time-symmetric, and yet, in our everyday macroscopic world, time is clearly not symmetric. Ice cubes melt into a puddle, but you'll never see a puddle spontaneously form back into an ice cube. An egg breaks, but it never unbreaks itself. Smoke disperses from a chimney, but never gathers itself back down. This one-way street of events doesn't come from the fundamental laws. It comes from the starting conditions. The universe began in an extraordinarily low entropy state. This is one of the deepest mysteries in cosmology. At the Big Bang, all the matter and energy were distributed in a remarkably smooth and orderly way. That smoothness was a state of incredibly low entropy. And ever since that special beginning, the total entropy of the universe has been increasing. This constant, unstoppable increase is what paints the arrow of time across the cosmos. Your own memory is a direct consequence of this process. To form a memory, your brain has to create a physical record. Neurons fire and form new connections. Molecules rearrange themselves. And in this process, heat is released. All of these actions increase the total entropy of the universe. The past leaves traces memories because entropy has already increased in that direction. The future, however, has no traces yet because entropy hasn't increased that way for you. This creates a powerful illusion. The past feels fixed, solid, and real. The future feels open, uncertain, and yet to be written. But this is really an asymmetry of information, not an asymmetry of existence. If the universe is a block where all of past, present, and future exist simultaneously, then the only reason the past feels different is that it's the part that has left a record you can access. This is a critical distinction. Time's arrow isn't built into the fabric of space-time. It's a product of how information gets stored and processed. Your brain is essentially an entropy-producing machine. Every single thought you have, every decision you make, every memory you form consumes energy and increases the overall entropy of the universe. Consciousness itself seems to depend on these irreversible processes, which is why your awareness is always oriented towards what we call the future. You anticipate what's next because it's useful for survival. You remember the past because those lessons improve your chances. Both of these abilities rely on the entropy gradient. If entropy wasn't increasing, you wouldn't experience the flow of time at all. This completely reframes why the universe feels so dynamic and alive. It feels that way because we are complex systems embedded within this cosmic flow of increasing entropy. We are literally riding the wave of time's arrow. But this just pushes the big question one step further back. Why did the universe begin in such an improbable low-entropy state in the first place? This is one of the most profound, unsolved problems in all of physics. If high-entropy states are statistically so much more likely, then a low-entropy beginning is unbelievably rare. So why did it happen? Some physicists argue it's just a brute fact of our universe, with no deeper explanation needed. Others look to cosmology for answers. A theory called cosmic inflation, a period of hyper-fast expansion in the very early universe, might explain why things started out so smooth and ordered. But even inflation seems to require its own special starting conditions, so it doesn't completely solve the puzzle. Another mind-bending idea is that our universe is just one of many in a vast multiverse. In this grander cosmic landscape, different universes might have different histories and different entropy rules. We, of course, find ourselves in a universe with a low entropy beginning because that's the only kind of universe where complex structures like galaxies, stars, planets, and observers like us could ever form. This idea is controversial, but it points to an amazing possibility that the arrow of time isn't fundamental at all. It might be environmental, just like gravity feels different depending on where you are. The direction of time might just be a local feature of our particular patch of the cosmos. There's also a deep, strange connection between entropy and gravity. For most things, clumping together means less order or higher entropy, but with gravity, it's the opposite. A smooth, uniform cloud of gas has lower entropy than a star that has collapsed from that gas. And a star has much lower entropy than a black hole, which represents the maximum possible entropy for a given mass. This means the initial smoothness of the universe was an even more special state of low gravitational entropy than we thought. Why did gravity start out so tidy? Some scientists think the answer lies in new, undiscovered physics. Perhaps something related to quantum gravity and the very nature of space-time at the smallest possible scales. These are huge, open questions. But here's what we can say for now. The arrow of time that you feel every second of your life is unwritten into the fundamental equations of reality. It's written into the universe as starting conditions and the way information flows through physical systems like your own brain. Time isn't a river pushing you forward. It's more like a landscape with a slope, and you are constantly moving downhill along that gradient of increasing entropy. Thinking about it this way can feel profound. If the past still exists somewhere in space-time, then moments aren't truly lost forever. They're just inaccessible from your current position. Your childhood isn't gone. It's simply located at a different coordinate in space-time. Your future self isn't an imaginary phantom. It's another part of the whole structure. This doesn't take away the meaning of life. For many, it deepens it. Moments matter, not because they vanish, but because they are permanent parts of this grand four-dimensional tapestry. From inside, experience unfolds, moment by moment. From a hypothetical outside view, everything is already there. Both perspectives are valid. The universe doesn't contradict your experience. It gives it a much larger context. For now, just rest with this idea. Time seems to flow because entropy increases. Entropy increases because the universe began in a very special, orderly state. And your awareness, your very consciousness, exists because it rides that irreversible wave of change. Thanks for watching. So far on our journey through time, we've seen its certainty begin to crumble. We've learned the universe doesn't need a flowing present, that the arrow of time isn't fundamental, and that past and future simply coexist. But now we're going deeper, to a layer so strange that time itself becomes unstable. Welcome to the world of quantum mechanics. Quantum mechanics doesn't just challenge our intuition, it dismantles it completely. Down at this tiny, bizarre scale, events don't always happen in a definite order. Cause and effect, the bedrock of our daily lives, can become a fuzzy, blurred mess. It's a place where asking which came first sometimes has no meaningful answer. This isn't just philosophy, it's physics, proven by experiment. In our classical world, if event A causes event B, then A must happen before B. The order is absolute. But quantum systems are different. They can exist in a state of superposition, just as a single particle can be in two places at once. An event can be in a superposition of happening both before and after another event. It sounds impossible, I know, but physicists have actually created situations where two quantum operations occur without any definite causal order. The system behaves as if A causes B and B causes A at the same time. It's only when we measure it that a specific order snaps into place. This is called indefinite causal order, and it tells us something profound. The order of time isn't fundamental. It's an emergent property that appears only when quantum possibilities collapse into our familiar classical reality. At its deepest level, the universe doesn't always care about before and after. This forces us to rethink what time even is. In classical physics, time is just a background clock, ticking away steadily. In Einstein's relativity, it becomes part of a flexible spacetime, dependent on the observer. But in quantum mechanics, time gets even weirder. It's often treated as an external parameter, not a physical quantity you can measure, like position or momentum. And this creates a huge tension. Everything else in the quantum world is quantized. It comes in discrete packets. Energy, momentum, even entire fields are quantized. But time isn't. Why? The problem is that quantum mechanics assumes a fixed background time to operate against. But general relativity tells us that time is dynamic, warped, and shaped by matter and energy. When you try to merge these two monumental theories into a single theory of quantum gravity, time becomes a massive headache. This is famously known as the problem of time. In many attempts to quantize gravity, time simply vanishes from the fundamental equations. The most famous example is the Wheeler-DeWitt equation, which tries to describe the quantum state of the entire universe. And guess what? There's no time variable in it at all. The universe, at its most fundamental level, is described by a timeless state. This is deeply unsettling. If the universe's ultimate rulebook has no time in it, how does anything happen? How does change occur? How do we experience the flow of life? Many physicists believe the answer is that time is emergent. It isn't a fundamental feature of reality. Instead, it arises from the relationships and correlations between different parts of the universe. Imagine the universe as one giant, static, quantum state. Within that state, different subsystems can be entangled in such a way that one part can act as a clock for another. Change isn't absolute, it's relational. Time isn't something the universe has asterisk. It's something that systems measure relative to each other. Physicist Julian Barber champions this idea. In his view, the universe is a vast collection of timeless snapshots he calls nows. Each one of these configurations exists independently and eternally. The feeling of time passing, of a flowing story, arises because some of these nows contain records or memories of others. A configuration that contains a memory of another one will perceive itself as being later. Time isn't flowing. It's just that patterns and records are embedded within this static cosmic structure. It's a radical idea, but it aligns disturbingly well with what modern physics is telling us. The feeling of change is an illusion created by how information is arranged. Until a measurement is made, a system doesn't have definite properties. Events aren't fixed until an interaction happens. Even the order of time can be indeterminate. It's only when countless quantum events interact with their environment and decohere, locking into classical states, that a stable, flowing time seems to appear. Decoherence is the key. When a quantum system's superpositions collapse due to environmental interaction, information leaks out, entropy increases, and our classical reality emerges. Before decoherence, there's no clear past or future. After decoherence, records exist, memory exists, history exists. This suggests that time didn't begin at the Big Bang. Instead, it began when the universe became classical enough for stable records to form. Time is not fundamental. History is not fundamental. Reality only becomes historical after decoherence. This has huge implications for cosmology. In the fiery furnace of the early universe, just fractions of a second after the beginning, everything was pure quantum chaos. There were no stable structures, no observers, no records. In such a universe, the very concept of time might have been meaningless. Only after the universe expanded and cooled, allowing decoherence to happen on a grand scale, did classical spacetime and the time we know emerge. Asking what happened before that might be a meaningless question. If time itself emerges within the universe, then the universe didn't begin in asterisk time. Time began in asterisk the universe. It's like asking what S north of the North Pole. The question assumes a framework that simply doesn't apply there. Quantum mechanics also has a strange symmetry, time reversal. At the microscopic level, most laws of physics work just as well forwards as they do backwards. And yet, we never see time run in reverse. We never see a broken glass reassemble itself. Why not? Because that would require entropy disorder to decrease, which is overwhelmingly improbable on a large scale. But here's the quantum twist. On very small scales, and for very short moments, quantum fluctuations can allow entropy to decrease locally. This means that at the tiniest levels of reality, the arrow of time isn't a strict law. It flickers. Its direction becomes a statistical average, not an absolute rule. The arrow of time is emergent, fragile, and depends on the scale you're looking at. At our scale, it's rigid. At the quantum scale, it dissolves into uncertainty. Some physicists take this even further, proposing that at the ultimate smallest scale, the Planck scale, time doesn't exist at all. Instead, there's just a network of quantum relationships with no temporal ordering. In this view, both space and time emerge together from something even more fundamental. And causal set theory, where reality is a sprinkle of discrete events, and time emerges from their causal links. The message from all these cutting-edge ideas is consistent. Time is not a basic ingredient of the universe. It's something that's constructed. This has profound implications for causality. We assume causes must precede their effects. But if the ordering of time itself is emergent, then causality might be emergent too. At the quantum level, cause and effect can blur into one. At our classical level, they solidify into a strict sequence. This doesn't mean reality is random chaos. It means that the order we cherish emerges from a deeper, more symmetric reality. Think of it like temperature. An individual atom doesn't have a temperature. Temperature is a property that emerges from the collective motion of many atoms. Time may be similar. It emerges when enough parts of the universe interact to create stable records and a clear gradient of entropy. Your personal experience of time is real, but it's not a universal truth. It's a local, conditional, and ultimately fragile phenomenon. You are not a traveler moving through time on a fixed road. You are a complex pattern that exists within the block of space-time. Your consciousness is simply sampling different slices of that pattern in a sequence, creating the internal feeling of flow. The universe itself isn't rushing forward. It simply is, containing all moments at once. Time is not a river. It is not a force. It is not a thing that flows. It is a relationship. And relationships only exist when systems interact. What does this mean for our own experience? Next time, we will explore how this timeless foundation of reality connects to consciousness itself. We'll ask whether awareness depends on time, and whether consciousness might be the very process that makes time feel so real. If time isn't a fundamental part of the universe, why does it feel so incredibly real? Why does every single moment of our awareness seem anchored to a present that's always moving forward? Why does our consciousness feel so inseparable from the passage of time? To even begin answering this, we have to be careful. Physics, as it stands today, doesn't really have an explanation for consciousness. But what it can do is tell us something vital about the conditions where consciousness happens. And here's the key. Consciousness depends on change. Imagine a perfectly static, unchanging system. Could it be aware of anything? No. Awareness requires differences, contrasts, transitions. Thoughts pop into your head because the states of your neurons are changing. You perceive the world because signals from your senses arrive, get processed, and are compared to what came before. Memories form because the physical structures in your brain are altered in a lasting way. Every single one of these processes relies on something called irreversibility. This is the secret ingredient. Irreversible processes are those that increase entropy, the measure of disorder in a system. Once they happen, you can't just rewind the tape. Think about it. A neuron firing, a synapse strengthening, a chemical signal being released, all of these are one-way streets. They leave a mark, they leave a trace. And these traces, that's what memory is. But memory isn't like a passive video recording. It's an active, physical restructuring of matter. When you remember your first day of school, your brain isn't pulling up a perfect digital file of the past. It's reconstructing an experience using neural pathways that have been physically shaped by that increase in entropy. This is why memory is fundamentally asymmetric. You remember the past because the past has already happened, increasing entropy and creating those physical records in your brain. The future hasn't. It's a blank slate, entropically speaking. Our entire conscious experience is built from this foundation, a blend of memory and anticipation. You remember what's happened, and you predict what might happen next. Both of these abilities rely on this entropy gradient. This continuous process of recording the past and predicting the future is what creates the powerful sensation of time flowing forward. But here's the mind-bending part. This feeling does unrequire time itself to be a fundamental, flowing river. It only requires a system, like our brain, that's embedded in an entropy gradient and processes information in a sequence. You don't experience the entire four-dimensional block of space-time all at once. You experience a path through it, one moment at a time. Your consciousness isn't the universe unfolding, it's a localized process, sampling states in a very specific order. This is why the present moment feels so special and privileged. The now is where memory formation happens. It's the moment where irreversible processes are occurring, where information is being converted into physical structure. From a physics perspective, the present isn't a single, infinitesimal point in time. It's a process. Neuroscience backs this up. What you perceive as now isn't instantaneous at all. It's actually an integration window. Your brain gathers sensory input over a short span of time, maybe tens or even hundreds of milliseconds, blends it all together, and presents it to you as a single, coherent experience. Within this window, the light from an object might reach your eyes before the sound of it reaches your ears. Yet you experience them as happening at the same time. This illusion of simultaneity is constructed by your brain. Your brain isn't a clock that's simply reading some external, universal time. It's an active organizer, creating the very sense of temporal order you experience. So, the feeling of now isn't a feature of the universe. It's a feature of your neural processing. This idea gets even clearer when we look at altered states of consciousness. In dreams, time goes haywire. Entire sagas can play out in just a few seconds of sleep. Cause and effect get jumbled up. The sense of a continuous timeline can completely fracture. Or consider deep meditation. Practitioners often report that the sense of time passing can diminish or even disappear entirely. Moments feel stretched out, infinite. The nagging pull of the past and the anxious anticipation of the future just fade away. And in certain neurological conditions, where people lose the ability to form new memories, their present doesn't seem to move forward. Their experience gets stuck in a strange, repeating loop. What all these phenomena reveal is something profound. Our experience of time depends on how our consciousness is structured, not necessarily on how the universe is structured. If consciousness can exist with a completely altered perception of time, then our normal perception of time can't be fundamental. It has to be constructed. This leads us to a stunning possibility. Maybe time, as we experience it, only emerges when systems like brains exist. Without an observer capable of creating memory and anticipating the future, the universe would still exist in all its four-dimensional glory, but the experience of time wouldn't. There would be no flow, no now, only a static, unchanging structure. This doesn't mean the universe needs us to exist. It means the experience of time needs us. The block universe doesn't care if it's being observed, but the sensation of moving through it, of living a life from moment to moment, absolutely does. This reframes that old philosophical question. If a tree falls in a forest and no one is around to hear it, does it make a sound? Well, what if we ask, does time exist without an observer? Physics seems to hint that the answer might be no, at least, not in the way we feel it. The events exist, the relationships between them exist, the correlations exist. But the feeling of time passing, of a river flowing from past to future, that only arises when an information processing system like a brain gets to work within an entropy gradient. This is why consciousness and time are so intimately linked. But there's another layer to this. Consciousness doesn't just experience time, it gives time meaning. Without meaning, a sequence is just a sequence. One thing happens, then another. So what? What makes moments feel significant is how they relate to our goals, our values, our fears, and our hopes. These are all cognitive constructs layered on top of the physical processes. This is why 5 minutes waiting for a scary medical result can feel like an eternity, while 5 hours spent with people you love can flash by in an instant. The universe isn't speeding up or slowing down because you're bored or engrossed. Your experience of it is. You are real because your state exists within that grand structure. Your experiences matter because they are indelible patterns etched into the fabric of reality. But it suggests that our existence isn't just a fleeting spark that vanishes into nothing. This idea can be emotionally challenging, but there's a strange comfort in it too. Nothing is truly rushing away from you. Nothing is slipping through your fingers. The universe isn't some cosmic conveyor belt dragging everything into oblivion. It's a vast, intricate structure that contains everything that ever happens. Your life isn't a line that vanishes behind you as you walk. It's a region of space-time that exists eternally. This doesn't make suffering less painful or joy less precious. It makes them a permanent part of reality's tapestry. Sequence requires memory. Memory requires entropy. And entropy requires an asymmetry between past and future. That asymmetry isn't time itself, but perhaps it's the shadow that time casts. Thanks for watching. If consciousness gives time its feeling of motion, then gravity shows us where that feeling breaks down. And there's no place in the universe where time becomes more fragile, more distorted, and more uncertain than near a black hole. Black holes aren't just extreme objects. They are cosmic laboratories where the basic assumptions we make about time quietly fail. A black hole begins with something pretty ordinary, a massive star. It lives its life, burning nuclear fuel in its core. But when that fuel runs out, the outward pressure stops. Gravity wins. The star collapses in on itself. If the star is massive enough, nothing can stop this collapse. At a certain point, an event horizon forms around this collapsing core. Now, the event horizon isn't a physical surface. You can't touch it. It's not a wall. It's a boundary in space-time itself, a point of no return. Once you cross it, no signal can ever escape back out, not even light. This alone should make us feel a little uneasy. Light defines cause and effect. It defines what can influence what. So, if light can't escape, neither can information. But the strangest thing about black holes isn't what happens inside. It's what happens to time at the boundary itself. For someone watching from far away, time near the event horizon seems to slow down. An object falling toward a black hole would appear to move slower and slower. Its clock would tick more and more sluggishly. As it gets closer and closer to the horizon, it would seem to freeze in place. From our distant perspective, the object never actually crosses the boundary. And this isn't some optical illusion. It's real gravitational time dilation. Its own clock ticks normally. It feels nothing special as it crosses the horizon. No alarms go off. No walls appear. Locally, the physics feels completely ordinary. The answer is both. This isn't a paradox. It's relativity. Time isn't universal. It's local. The event horizon is a place where the disagreement between observers becomes absolute. One person says the crossing never happens. The other says it already did. There's no single global answer. This fact alone suggests that time can't be a fundamental feature of the universe. If it were, all observers would have to agree on the sequence of events, but they don't. Inside the black hole, according to classical general relativity, things get even weirder. Time and space essentially switch roles. The direction that once pointed forward in time now points inward, toward the singularity at the center. The singularity isn't a place in space you can visit. It's a moment in time, a future moment that is absolutely unavoidable. Once you're inside, you don't fall toward the singularity. You fall forward into it. This language is important. Inside a black hole, reaching the singularity is as inevitable as reaching tomorrow is for you right now. You can't stop it. You can't turn around. The future is geometrically fixed. This is what extreme gravity does to the very structure of time. But this is also where our best theory of gravity, general relativity, breaks down. At the singularity, densities become infinite. Space-time curvature becomes infinite. Time and space as we know them lose all meaning. Our physics just stops working. This tells us something critical. Our current theories can't describe time everywhere. If time were truly fundamental, our best theory would be able to handle it consistently. But it can't. This is where quantum mechanics has to step in. Quantum theory tells us that infinities are warnings. They signal that our theory is missing something. They tell us we've pushed a theory beyond its limits. At the center of a black hole, a new theory, quantum gravity, must take over. And when quantum gravity enters the picture, time itself might disappear entirely. Many approaches to quantum gravity suggest that singularities don't actually exist. The density becomes enormous, but it's finite. Space-time doesn't tear, it just reorganizes itself. If this is true, then the inside of a black hole isn't an endpoint. It's a region where space-time behaves in ways we don't yet understand. Some theories suggest black holes might bounce, creating entirely new regions of space-time. What matters for our discussion is this. In all serious attempts to describe what happens, classical time ceases to be meaningful inside. There is no universal clock ticking away inside a black hole. Time fragments. This gets even stranger when we consider Hawking radiation. It turns out black holes aren't eternal. They slowly evaporate. Tiny quantum fluctuations near the event horizon cause particles to escape. Over incredibly long time scales, the black hole loses mass and eventually disappears completely. This introduces a deep puzzle known as the black hole information paradox. If something falls into a black hole, and then the black hole later evaporates, where does the information about that object go? But if the information escapes, how does it get out from behind an event horizon? Resolving this paradox seems to require abandoning at least one of our most deeply held beliefs about the universe. Either the idea of locality fails, meaning events aren't just influenced by their immediate surroundings, or time behaves very differently than we think. Or maybe both. Many physicists now believe that space-time itself emerges from something deeper, quantum information. The geometry of space and the flow of time might arise from complex patterns of quantum entanglement. In this view, an event horizon isn't a boundary in space. It's a boundary in information. The time inside the black hole and the time outside aren't separate timelines. They are just different ways of describing the same underlying quantum reality. This idea fits perfectly with something called the holographic principle. This principle suggests that all the information contained within a volume of space can be described by a theory that lives on the boundary of that space. For a black hole, the boundary is the event horizon. The amount of information a black hole can hold scales with its surface area, not its volume. This is shocking. It's like saying the contents of your room could be fully described by information written on the walls. It suggests the interior isn't fundamental. The boundary is. And if that's true, then time inside might not be fundamental either. The same logic can be applied to the entire universe. If space-time is emergent, then time is emergent. Black holes show us the limits of time. They show us regions where time slows, stops, flips direction, or loses meaning entirely. They are like warning signs written into the fabric of the cosmos, telling us that time isn't a universal stage for reality to play out on. It's a local construct. This has big consequences for ideas like the block universe, the notion that all of time past, present, and future exists simultaneously. If that block is real, then black holes carve strange and unknowable regions into it, places where our usual slicing of time into past, present, and future becomes impossible. The block isn't a simple, static crystal. It's a complex, dynamic, quantum object. Your personal experience of time happens far from these extremes, in weak gravity and at low energies, where space-time behaves gently. Here, time feels smooth and continuous, but the universe doesn't promise us this experience everywhere. This brings us closer to a radical conclusion. Time may not be fundamental anywhere. If so, then the deepest description of reality might contain no time at all, only relationships, only correlations, only structure. The feeling of temporal flow that we experience arises when certain patterns repeat and evolve in ways that our consciousness can order sequentially. We latch onto those patterns, but the universe itself doesn't flow. It simply contains. Black holes don't just bend space, they fracture our understanding of time. And in doing so, they reveal that time was never as solid as it felt. Thanks for watching, and be sure to subscribe for more explorations into the nature of reality. Did you know that black holes might be telling us that space and time aren't fundamental? That instead, the universe itself might be built from information? It sounds like science fiction, but stick with me, because this idea completely changes how we think about reality. In our everyday lives, we think of information as abstract data, numbers, messages. But in physics, information is physical. It has to be stored in physical systems, carried by matter or energy, and it must obey the laws of physics. For instance, there is a principle that says erasing even a single bit of information requires a minimum amount of energy and creates heat. Information isn't just something asterisk in asterisk the universe. It might be part of what the universe asterisk is asterisk. This idea really clicked into place when physicists studied black holes. They found something shocking. The amount of information a black hole can hold, its entropy, isn't proportional to its volume, but to the area of its surface, the event horizon. This is totally different from anything else in the universe. Imagine a library where all the books are stored, not on shelves inside, but on the walls of the building itself. This suggests that everything that ever fell into a black hole star's planets was encoded on its two-dimensional surface. The three-dimensional inside becomes secondary. This led to a mind-bending concept called the holographic principle. It's like watching a 3D movie. The depth you see is generated from a 2D screen. In this view, space itself emerges from information. And if space can emerge from information, then what about time? This is where it gets even stranger. A powerful mathematical tool, the ADS-CFT correspondence, shows how a universe with gravity, like ours, can be perfectly equivalent to a quantum theory without gravity living on its lower dimensional boundary. In this model, the space and time we experience emerge from quantum interactions on that boundary. The boundary theory itself doesn't have time in the same way. It's as if space-time is a user interface, a convenient way for us to experience a much deeper reality governed by quantum information. We used to think of time's arrow as the direction of increasing entropy or disorder. Now, we can get more specific. The arrow of time might be the direction of increasing quantum entanglement. Entanglement is one of the weirdest and most profound features of quantum mechanics. It's a deep connection between particles. Once two particles are entangled, they don't have separate, independent states anymore. Measuring one instantly affects the other, no matter how far apart they are. It's like they're a single system. This process of spreading entanglement is effectively irreversible on a large scale. The direction of time that we experience might simply be the direction in which the universe becomes more and more entangled. In this view, time doesn't flow like a river. It's a measure of the universe's total entanglement. To go backward in time would mean unentangling everything, gathering all the scattered information from the environment and putting it back exactly where it was. It's not physically forbidden, but it is so astronomically improbable that it might as well be impossible. So how does this relate to you, to your consciousness? Your brain is a magnificent information processing machine. It takes in sensory data, integrates it, stores memories, and guides your actions. Every thought, every perception, every decision involves processing information, which increases entanglement and entropy. Your feeling that time is passing is your awareness of this constant flow of information. The now you experience is always a reconstruction of events that have just happened, events that have already become part of the past by increasing the universe's entanglement. Some physicists take this idea to its ultimate conclusion. They propose that at the most fundamental level, the universe is a giant network of quantum bits interacting with each other. From the pattern of these interactions, everything we know emerges: space, time, particles, forces. In this model, time isn't an input, it's an output. The universe doesn't evolve in time. It just is a complete, timeless structure of relationships. We experience time because we are subsystems within that structure, and our memories are just asymmetrical correlations within the larger pattern. This is why equations in quantum gravity often seem to be timeless. They describe the whole structure at once. This perspective doesn't make reality abstract or meaningless. It means the fundamental components of our world are different from what we thought. Time might be the shadow that information casts as it becomes more and more entangled with itself. So the next time you feel a moment slip away, remember, you might not be moving through time. You might just be part of an ever-growing web of cosmic information. This is a huge idea to process, I know, but it suggests that the deepest layer of reality isn't matter or energy, but information itself. What if I told you the universe never began and will never end? This sounds crazy, right? We see beginnings and endings everywhere. Movies start and finish. We're born, we live, we die. But what if the universe, the whole cosmic shebang, plays by a completely different set of rules? What if our most basic ideas about time are just wrong? We're all familiar with the Big Bang. It's painted as this grand opening moment. Suddenly, there's space, time kicks off, and all the stuff that makes up galaxies, stars, and us bursts into existence. It's a powerful story, but it's also a bit of a fib. The Big Bang isn't some firecracker that went off at a specific spot. It's not even clearly a single moment in time. Really, it's more like a "Here be dragons" sign on our map of the cosmos. It's the point where our current theories, like Einstein's general relativity, just break down. Think of it like this. If you rewind the cosmic clock using Einstein's equations, everything gets hotter and denser. Galaxies rush back together, matter gets squeezed, and temperatures skyrocket. Eventually, the math spits out something impossible: infinite density, infinite heat, infinite everything. This is what physicists call a singularity. But here's the secret. Singularities aren't real things. They're error messages. They're the universe telling us, your theory is broken here. You need something better. And that something better is quantum mechanics. General relativity is great for big stuff, like planets and galaxies. But when things get incredibly tiny and dense, like the universe near the Big Bang, quantum effects take over. And at that scale, even space and time itself start to get weird and fuzzy. Classical, one-way time might not even exist there. This means the Big Bang might not be the beginning of time. It might be the moment where time itself emerged from a more fundamental, timeless reality. So, asking what happened before the Big Bang could be like asking what's north of the North Pole. The question itself doesn't make sense, because the concept of before doesn't apply. This isn't just a philosophical musing. It's a serious idea in physics. Some models suggest that near the Big Bang, the line between time and space blurs. There's no clear forward or backward. The universe doesn't start. It just transitions from a quantum, timeless state into the expanding, time-filled cosmos we know. Another popular idea is the Big Bounce. In this scenario, our universe is just the latest cycle. A previous universe contracted, got super dense, and then quantum gravity kicked in, acting like a cosmic spring that reversed the collapse and started a new expansion, our Big Bang. If this is true, the universe has no beginning and no end, just endless cycles of contraction and expansion. This is a tough pill to swallow. We're wired to look for a starting point, a first cause, a let there be light moment. But physics might be telling us that the universe doesn't have one. Instead of the universe beginning in time, time begins in the universe. It's a subtle but huge difference. Imagine the entire history of the universe, past, present, and future, as a single, complete object. Physicists call this the block universe. In this view, asking when the universe began is like asking where a circle starts. There's no special starting point. The Big Bang isn't an origin. It's just a boundary, a place where the rules of geometry change. And the same logic applies to the future. We think of the end of the universe, whether it's a heat death where everything fizzles out or a big rip, as something we hurtling towards. But in the block universe, the end isn't an event waiting to happen. It's just another region of space-time, already there, coexisting with our present moment. This doesn't mean everything is predetermined, like a movie you've already seen. Quantum mechanics still leaves room for randomness and uncertainty. But that randomness is itself part of the timeless fabric of the universe. The fundamental laws of physics aren't a to-do list for the cosmos. They're more like a set of rules that describe the relationships between all the parts, all at once. Time is just a tool we use to make sense of change from our limited perspective. It's how we read the story. Different people, moving at different speeds, can even disagree on the order of events. They're just slicing up the same four-dimensional block in different ways. So, if there's no beginning, what does that mean for questions like what caused the universe? Well, the very idea of a cause coming before an effect depends on time. If time itself is part of the universe, then the universe might not need an external cause. It could just be a self-contained, self-consistent structure that simply exists. The big question shifts from why did it begin to why does this particular structure exist instead of some other one. This can change how we see our own existence. If the universe isn't a countdown to an inevitable end, then our moments don't just vanish into the past. They remain part of the cosmic structure. Your experiences, your joys, your sorrows, they aren't erased as time moves on. They coexist with the future. This doesn't mean change isn't real. It just means reality doesn't annihilate the past. The universe isn't a story being written and then deleted. It's a complete book. We just read it one line at a time because that's how our consciousness works. The full text is already there. This lines up with cutting-edge ideas in quantum gravity, which suggest the universe can be described by a single, timeless quantum state. In this view, time emerges from the relationships between different parts of this state. The Big Bang isn't a moment. It's a region of this state with certain properties. The future isn't a destination. It's just another set of relationships relative to where you are now. Everything exists in relation to everything else. But where do we fit in all this? If our lives are finite in a timeless universe, what does that mean? It means your life is a specific pattern within this grand structure. It has a beginning and an end in the sense that your consciousness, your awareness, is tied to a functioning physical body. But the pattern itself, the melody of your life, is a permanent part of the cosmos. A wave on the ocean exists even after it crashes on the shore. Its form, its energy, was real. Your life is like that. In a timeless universe, completion doesn't mean erasure. It means your existence has a location in space-time, and that location is forever part of the whole. This perspective can be either deeply unsettling or incredibly calming. Physics doesn't tell us how to feel. It just shows us what's possible. And what seems possible is a universe that doesn't flow, doesn't start, and doesn't end in the simple way we assume. It just is. And within that timeless is, we get to experience the beautiful illusion of a journey. Of course, this raises some very deep questions. If the universe is a timeless block, what does that mean for free will? Are our choices real, or are we just tracing a path that was already laid out? We'll dive into that mind-bending topic next time. For now, let this idea settle. The universe may not have a beginning. It may not have an end. It may simply be. Thanks for watching. If you enjoyed this journey into the nature of time, don't forget to like, subscribe, and hit that bell so you don't miss our next video. See you then. If the universe doesn't flow in time, if the past and future coexist within a single vast structure, a profound question surfaces. It's not a technical question. It's deeply personal. It asks, is choice real? Do our decisions actually matter? Does free will survive in a universe that already contains everything that will ever happen? This question has haunted philosophers for centuries, but modern physics sharpens it into something we can't ignore. In what physicists call a block universe, all events exist simultaneously. Your birth exists. The conversations you'll have next week exist. Your final moments exist. From an outside perspective, this entire structure of space-time looks complete, already written from beginning to end. Seeing it this way, it's tempting to conclude that free will must be an illusion, but this conclusion is too quick. It makes a huge assumption that for a choice to be real, the future must be fundamentally open and unwritten. But physics doesn't actually support this idea. Free will isn't about whether the universe already contains your decisions. It's about how those decisions are generated. A choice is free if it comes from your own internal processes, your thoughts, your values, your memories, rather than from some external force pushing you around. None of this disappears just because the choice already exists as an event in space-time. Think about it like this. Your decision to raise your hand tomorrow exists as a space-time event, but it exists because you will decide to do it. From inside your own experience, deliberation feels completely real. You weigh your options. Different reasons compete in your mind. The outcome feels uncertain because you don't yet know which of your internal processes will win out. This uncertainty is about your knowledge, not about the fundamental nature of reality. But that's all you need for a choice to feel meaningful. The block universe isn't saying you're a puppet on a string. It's saying you are a pattern within the fabric of space-time, and your choices are an essential part of that pattern. This isn't the same as fatalism. Fatalism is the idea that things will happen no matter what you do. The block universe says the opposite. Outcomes happen precisely because of what you do. That distinction changes everything. Imagine watching a recording of a chess game. The entire game exists on the recording, from the first move to the last. Every move is fixed. But within the game, each move was made based on the player's strategy and thinking. The fact that the game is recorded doesn't make the player's choices unfree or meaningless. In the same way, the fact that your life exists as a complete structure in space-time doesn't mean your choices are irrelevant. They are the structure. Another way to understand this is through causation. In physics, causes aren't pushes from the future. They are relationships within the existing structure. Your brain state at one moment causes your action in the next moment. That causal link is real. regardless of whether the whole timeline exists all at once. Your action depends on your decision, which depends on your beliefs and desires. These dependencies are what matter, not some magical flow of time. Whether the universe is deterministic or probabilistic, free will is about where our actions come from, not about whether the future is metaphysically open. The block universe might contain all possible outcomes, each one realized in a different branch of reality. Your experience simply follows one of these branches. This doesn't eliminate choice, it reframes it. You don't choose which universe you're in, but your actions determine which branch of reality you experience. Your choices are the moments where possibilities collapse into a single recorded history. This brings us back to information. A decision is a process that increases entropy. Your neural activity changes, energy is used, and a record is formed in your brain and in the world. Once made, a decision can't be undone. This irreversibility is what gives our choices weight. From the outside, the record of your choice simply exists. From the inside, you are creating it. Both perspectives are true. The feeling of freedom we have arises because our consciousness doesn't have access to the whole picture. We only experience our local corner of space-time. We don't see the entire block. This ignorance isn't a flaw. It's what makes being an agent possible. You'd just be an observer, watching your life unfold. Evolution, selected for organisms embedded in uncertainty, not for omniscient spectators. This understanding also preserves moral responsibility. You are responsible for your actions because they come from you, from your character, your reasons, and your values. They aren't imposed on you by the future. Think about regret. Regret is based on the idea that things could have been different, and in a sense, they could have. Different internal states, if you had known something else or felt differently, would have led to different actions. Regret is our way of exploring those counterfactuals. The fact that an outcome is fixed does erase the meaning of the alternatives that were unrealized. This even clarifies how ethics works. The purpose of praise and punishment isn't to fight against fate, it's to shape the patterns of future behavior. By providing consequences, we influence the internal states that lead to decisions. We are shaping the patterns within the block universe. But what about a deeper worry? If the future already exists, does that mean our suffering is eternal? This is a common fear, but it comes from a misunderstanding. When we say a moment exists forever in space-time, we don't mean it lasts for an infinite duration. We mean it has a permanent location. A painful moment exists at a particular coordinate in space-time. It doesn't keep hurting after it's over. Your experience of that pain is finite. The fact that the moment exists doesn't mean you are trapped in it. It's located, not ongoing. By the same token, a moment of joy isn't fleeting because it vanishes. It's complete because it exists permanently as part of your life's pattern. This perspective doesn't mean we should become passive. Your future experiences still depend on what you do now. The arrow of cause and effect remains intact within the structure of space-time. Free will survives, not by fighting against physics, but by being a fundamental part of it. You aren't an outsider pushing against the universe. You are the universe, expressing itself through your choices. This dissolves a false choice we often make. Either the universe is a cold, mechanical machine and free will is an illusion, or free will is real and our understanding of physics must be wrong. The truth is, they operate at different levels of reality. Agency emerges from the complex patterns of life, just as life emerges from chemistry. These are layers of reality, not illusions. So, let's look at time one last time in this light. You experience the flow of time because you are a decision-making system. Your sense of the future is your awareness of possible actions. Your sense of the past is the record of your outcomes, and the present is the moment where deliberation happens. Even in a timeless universe, deliberation is real, and it is deliberation that gives our lives meaning and urgency. Free will doesn't require time to flow. It just requires our reasons to matter, and they do. They shape the beautiful, intricate, and complete pattern of reality. Thanks for watching. If this sparked some new thoughts for you, consider liking the video and subscribing for more explorations into the biggest questions of our existence. After confronting free will inside a timeless universe, we arrive at a question that feels almost inevitable. If time doesn't fundamentally flow, if space emerges from information, if causation survives without becoming, then what exactly is the universe? Is it a process, or is it something closer to a completed structure? One increasingly serious idea in modern physics is that the universe resembles a computation, not a computer running in time, but a logical structure defined by relationships between states. This doesn't mean the universe is literally a machine. It suggests that the laws of physics behave more like constraints than instructions. In an ordinary computer, computation unfolds step by step. One state follows another according to rules. This seems to require time. But a mathematical computation doesn't require execution. A completed proof exists all at once. Every step is logically connected. Nothing flows. The structure is static, yet it encodes a process. The universe may be more like that. The equations of physics don't tell the universe what to do next. They define which configurations are allowed and how they relate. The full set of allowed configurations forms a structure. Our experience of time is simply our journey through that structure. This view fits naturally with the block universe concept. The block isn't a frozen movie. It's a relational object. Every event is linked to others by lawful relationships. From within, those relationships feel like evolution. From outside, they are simply consistency. This distinction matters. If the universe were literally running, it would need an external clock, something outside space-time ticking away. But physics offers no evidence for such a thing. Every known physical clock is internal, measuring change relative to other changes. There is no master clock. This strongly suggests that time isn't something the universe uses. It's something observers use. Now, consider another idea closely related to computation: the universe as a self-consistent pattern. A self-consistent pattern is a structure that contains no contradictions. Every part fits with every other part according to its rules. Nothing needs to change for the pattern to exist. It simply is. Think of a crystal lattice. Each atom sits precisely where it must sit relative to the others. The universe may be like an immensely complex lattice, not of atoms in space, but of events in spacetime and correlations in quantum information. In this picture, the laws of physics aren't dynamic forces. They are constraints ensuring consistency across the whole structure. This perspective dissolves a common misconception. We often imagine laws as things that act on matter. But in modern physics, laws are relationships. They don't push, they describe. Gravity doesn't pull objects forward in time. It shapes space-time geometry, and objects follow that geometry. Quantum mechanics doesn't cause randomness. It describes a probability structure. And time is not a river that carries events along. It's a way of labeling relationships. When we stop treating laws as actors and start treating them as constraints, the timeless picture becomes much more natural. Let's go back to computation for a moment. A computation can be represented as a static object. For example, a truth table contains all possible inputs and outputs at once. Nothing happens inside the table, yet it encodes behavior. Similarly, the universe may encode all behavior within its structure. This doesn't trivialize our experience. It explains it. Experience is what it feels like to be inside such a structure with limited information. You don't see the whole truth table at once. You see one line at a time. And that line feels like time. This idea also explains why the universe appears so mathematical. Why do equations work so well? Why can reality be described in terms of symmetry, invariance, and structure? It's because mathematics is the language of relationships, independent of time. Physics seems to reveal that reality itself is fundamentally relational. Change, motion, causation, and time are all internal perspectives arising from our limited access to the whole. Now, let's consider one of the most disturbing implications of this view. If the universe is a complete structure, then nothing truly new ever comes into existence. Novelty exists only relative to an observer who has not yet encountered a particular region of the structure. From your perspective, tomorrow is new. From the universe's perspective, it's simply elsewhere. This doesn't make novelty meaningless. It makes it relational. Discovery isn't about creating facts. It's about encountering them. Life itself might be like this. Your life isn't a process unfolding from nothing into something. It's a region of the universe that exists. This doesn't rob life of its drama. It explains it. Drama arises from ignorance of the whole. If you knew the entire story in advance, there would be no suspense. The universe doesn't deprive you of suspense. Your perspective creates it. This viewpoint also clarifies why physics can sometimes feel emotionally cold. Physics doesn't speak the language of becoming. It speaks the language of being. The mistake is trying to force one to replace the other. Let's return briefly to the Planck scale, where many of these ideas converge. At the Planck scale, spacetime may not exist as a smooth manifold. It might break apart into discrete relations. In such a regime, the idea of continuous time loses all meaning. Instead, there may be fundamental transitions, not ordered in time, but ordered logically. Quantum gravity research often replaces time with ordering relations. One event is related to another, not by before and after, but by constraint. This is why time vanishes from so many fundamental equations. Time isn't missing. It's just unnecessary at that level. Only when systems become large and complex does a notion resembling time emerge. This emergence is robust. It works extraordinarily well. That's why our clocks work. That's why causation feels so reliable. But it's not fundamental. This layered view of reality is uncomfortable because it undermines a deeply held intuition that the universe is happening. Physics increasingly suggests that the universe isn't happening, it's structured. This doesn't mean nothing matters. It means meaning arises locally. Your values matter because they shape the local structure. They influence what happens in your region of space-time. The universe doesn't care. But the universe doesn't need to care for care to exist. Care is a pattern. Now consider a final subtlety. If the universe is a complete structure, is there any room for surprise? Yes. Surprise exists for embedded observers like us. You can be surprised even if the outcome already exists, simply because you don't know it. Surprise isn't about novelty in the universe. It's about novelty in your knowledge. This distinction preserves a sense of wonder. The universe can be complete and still be endlessly surprising. We can see a pattern emerging across all these ideas. Time emerges from entropy. Entropy emerges from information dispersal. Information emerges from quantum correlations. Space and time emerge from information. Choice emerges from structure. Meaning emerges from relation. Nothing fundamental flows. Everything relates. In our next exploration, we will approach the quietest and perhaps most unsettling conclusion of all. If the universe is timeless and complete, then death is not disappearance. It is relocation. Consciousness doesn't continue, but existence does. We will explore what this means without mysticism, comfort, stories, or despair. For now, let this part settle gently. The universe may not be running. It may not be evolving. It may simply be consistent. And inside that consistency, experience finds its path. Thanks for watching. After our journey from the human scale all the way down to the Planck length, it's clear this idea isn't just about physics. It quietly reshapes how we think about existence itself. The smallest possible scale forces us to reconsider what it means to be part of the universe. At first glance, the Planck length seems distant, almost irrelevant to our everyday lives. It's trillions of times smaller than an atom, far beyond anything we can ever touch or see directly. And yet, everything we experience, everything we are, is built upon it. Every single particle, every force, every moment of time emerges from processes operating at this unimaginably tiny scale. This brings a humbling realization. We often see ourselves as separate from the cosmos, observers living on a small planet in a vast, empty universe. But when you look at the deepest level, there is no separation. The same quantum fabric that governs the smallest distances also weaves together the largest galaxies. The same fundamental rules shape both the inner workings of an atom and the grand evolution of the entire cosmos. You are not an object placed inside the universe. You are a pattern formed by it. Think about it this way. Your body is made of atoms. Those atoms are made of particles, and those particles are really just excitations in quantum fields. Those fields only exist because spacetime itself allows them to. And spacetime, as we understand it, only exists because of the structure at the Planck scale. Everything connects downward, all the way to the same foundation. This means that incredible complexity can arise naturally. The universe doesn't need a special set of instructions to create structure. Given a few fundamental laws and enough time, simple rules generate an astonishing richness. Galaxies form, stars ignite, chemistry emerges, life appears, consciousness develops, and all of it, every last bit, rests on the quiet, underlying stability of the smallest scale. The Planck length also reframes how we think about limits. We usually see limits as failures, as a sign that our knowledge has hit a wall. But in physics, limits often reveal a deeper, more profound order. The speed of light, for example, is a limit on how fast we can travel. But it's also what makes causality possible, ensuring cause always comes before effect. Absolute zero is a limit on how cold something can get, but it's what defines the entire field of thermodynamics. In the same way, the Planck length may limit our ability to measure things with infinite precision, but in doing so, it defines the very resolution of reality itself. It tells us that not everything can be known in the way we might expect, and that's not discouraging. It's clarifying. It's a reminder that understanding doesn't require total domination or control. We don't need to access every single scale of the universe to appreciate its beauty. We just need to recognize the incredible patterns that emerge from its fundamental rules. At our human scale, the universe seems quiet and slow. Stars drift across the night sky. Geological changes take millions of years. But down at the Planck scale, the universe is a restless, chaotic, buzzing sea of quantum fluctuations, alive with uncertainty. Both of these descriptions are true. They are simply different views of the same reality, seen at vastly different resolutions. This also has a profound effect on how we think about time. Your life unfolds over decades. Civilizations rise and fall over millennia. Stars live for billions of years. Yet the fundamental ticking of reality's clock might be happening in intervals so small they make a nanosecond look like an eternity. The time that you experience, the flow of your life, is an emergent rhythm built from countless, lightning-fast microscopic changes. You are a slow, coherent process built from an impossibly fast, chaotic one. This perspective can be strangely comforting. It doesn't push human existence outside of physics. It places us deeply within it. Our thoughts, our awareness, our consciousness, they aren't some magical accident layered on top of a cold, indifferent universe. They are natural, predictable outcomes of physical law unfolding over immense scales of space and time. The Planck length doesn't make the universe feel smaller. It makes it feel deeper. It shows us that beneath apparent simplicity lies an extraordinary structure. Beneath stillness, there is constant motion. Beneath our illusion of certainty, there is fundamental probability. And yet, despite all this underlying complexity, the universe is remarkably stable. The same physical constants seem to have held true since the earliest moments after the Big Bang. The same structures persist. The same laws apply everywhere we've looked. This stability is what allows meaning to exist. If the universe were completely chaotic at every scale, nothing could ever endure. Nothing could grow or evolve. But because there is a smallest scale, a stable foundation, larger structures can form and persist long enough to matter, long enough for us to be here, thinking about it. In this sense, the Planck length is not just a limit. It is the foundation. It's the silent agreement that allows reality as we know it to exist at all. It's the bedrock upon which everything else is built. So far, we've looked inward, down to the smallest components of reality. But in the final parts of our exploration, we're going to look forward. We will ask what the future of physics might reveal about this fundamental scale. What new theories are being developed to probe this final frontier? We'll explore the tantalizing possibility that even the Planck scale is unto the end of the story. Could we one day understand what lies beneath space and time itself? The quest for that answer is one of the most exciting journeys in all of science. Thank you for watching, and I hope you'll join me as we continue to explore the deepest mysteries of our universe. Be sure to subscribe so you don't miss what's coming next. As physics marches onward, the Planck length stands as both a distant destination and a constant guide. It's not a finish line scientists expect to cross directly, but it silently shapes every question they ask and every path they explore. The future of fundamental physics, in many ways, is a long, intricate conversation with this tiniest of scales. One of the most promising avenues for this conversation comes not from building bigger machines, but from observing what's already out there. Humanity may never construct an instrument capable of directly probing Planck-length distances, but the universe itself is a grand, ongoing experiment. Extreme environments already exist, places where energy, density, and curvature push the very limits set by nature. Black holes are a prime example. Near the event horizon, gravity becomes unimaginably strong. Time slows to a crawl. Space itself stretches and in this extreme arena, quantum effects, usually confined to the subatomic world, start to play a significant role. While these regions are still a long way from the Planck scale, they might carry subtle signatures of quantum gravity. As our gravitational wave observatories, like LIGO and Virgo, become more sensitive, scientists will be listening more closely than ever to the cosmic symphony of black hole mergers. The final, violent moments before two black holes combine are governed by space-time curvature at its most extreme. Any tiny deviation from the predictions of classical general relativity could be a whisper from a deeper, more fundamental theory. Another window into this hidden realm lies in the very beginning of our universe. The theory of cosmic inflation, if confirmed in greater detail, could provide the clearest indirect glimpse into Planck scale physics. During inflation, the universe expanded at a staggering rate, stretching microscopic quantum fluctuations to cosmic proportions. These fluctuations are now imprinted on the cosmic microwave background radiation, the afterglow of the Big Bang. They might still carry the fingerprints of the fundamental rules that governed the universe at its birth. Future, more precise observations of the cosmic microwave background, polarization, and the search for primordial gravitational waves could reveal crucial information about energy scales approaching the Planck regime. These signals wouldn't give us the complete picture, but they would dramatically narrow down the possibilities for a theory of everything. While astronomers look to the heavens, theorists are looking inward, re-examining the very foundations of reality. A revolutionary idea is gaining traction. What if space-time itself isn't fundamental? Instead of trying to quantize gravity, what if gravity emerges from something deeper? This has led physicists to explore radical new connections between different fields, borrowing concepts from quantum information theory, thermodynamics, and even computation. Some of these new approaches suggest that the geometry of spacetime arises from intricate patterns of quantum entanglement. Imagine a vast network where the connections, the entanglement between quantum bits, create the very fabric of space and the force of gravity. Others propose that gravity isn't a fundamental force at all, but an entropic one, emerging from the universe's tendency towards disorder, much like how temperature emerges from the collective motion of atoms. If these ideas are on the right track, the Planck length might not be a physical boundary in space, but a boundary in our description of reality. It would mark the scale where the language of geometry breaks down and the language of information takes over. Asking what exists below the Planck length would be like asking what exists below a single bit of information in a computer program. The question itself loses its meaning because you've reached the fundamental unit of that system's description. There is nothing smaller within the language of that theory. And this is where another exciting technology enters the picture: quantum computing. As quantum computers become more powerful, they could allow us to simulate simplified models of quantum gravity. These simulations won't recreate our universe in a box, but they might reveal the fundamental principles of how space-time-like behavior can emerge from purely quantum systems. In fact, scientists have already used small-scale quantum systems to model aspects of the holographic principle and emergent geometry. As the technology advances, these simulations will become increasingly sophisticated, providing a powerful new tool to test these mind-bending theoretical ideas. Beyond these grand theoretical and observational frontiers, there's the relentless march of precision. Atomic clocks that lose only a second over the age of the universe, laser interferometers that can detect ripples in space-time smaller than the nucleus of an atom, and quantum sensors of astonishing sensitivity are constantly being improved. With each new order of magnitude in precision, we gain the ability to test physics in ways previously thought impossible. Even if direct Planck scale effects are incredibly suppressed and weak at our energy scales, they might leave faint, almost imperceptible traces that these ultra-precise instruments could one day detect. The history of physics teaches us that patience is a virtue. Phenomena once considered purely theoretical and forever unobservable, like the Higgs boson or gravitational waves, were eventually found through decades of persistence, ingenuity, and a refusal to give up. The Planck scale may follow a similar path. Its secrets might not be revealed through brute force, by smashing particles together at ever higher energies, but through subtle inference, by carefully piecing together clues from cosmology, black holes, and high-precision experiments. Alongside this scientific progress, a philosophical evolution is also underway. Physicists are becoming more comfortable with the idea that some questions might not have answers in the traditional sense we used to. Asking what lies below the Planck length might be like asking what lies north of the North Pole. The question itself is based on a framework, a continuous, smooth space that simply may not apply at that fundamental level. This isn't a sign of defeat for science, it's a sign of its refinement. Understanding the limits of our descriptions is a profound form of understanding in itself. The Planck length may be nature's way of telling us that reality is finite in its information content, relational in its underlying structure, and emergent in its geometry. It may be an invitation to abandon our intuitive idea of a perfectly smooth, continuous universe and embrace one that is fundamentally discrete, probabilistic, and built from information. If this is the case, the future of physics won't be about finding ever smaller building blocks. It will be about understanding deeper and more abstract patterns of connection and information. In the final part of our journey, we will bring all these threads together. We'll reflect on what the Planck length ultimately represents, not just as a concept in physics, but as a testament to human curiosity itself. We'll explore why this smallest of all possible scales might just be one of the most meaningful and profound ideas we have ever discovered. Thanks for watching, and be sure to subscribe for the final installment of our deep dive into the fabric of reality. As we approach the end of this journey, the Planck length starts to feel less like a technical detail and more like a message, a secret written into the very fabric of reality. It whispers a profound truth. The universe is not infinitely divisible. There is a point beyond which the questions we're used to asking simply stop making sense. For most of human history, we held a simple belief. If something was invisible, it was just too small or too far away. With better tools, we thought we could eventually see anything. But the Planck length throws a wrench into that idea. It suggests that some limits aren't temporary obstacles we can overcome with better technology. They are fundamental, permanent features of our existence. This is a monumental shift in our understanding. The universe might not possess infinite detail. Think about it. There could be a maximum resolution built into reality itself. Just like a digital photo is made of a finite number of pixels, our reality might be composed of fundamental, indivisible units of distinction. This doesn't make the universe crude or simplistic. On the contrary, it makes it incredibly precise. Precision doesn't need infinity. It needs consistency. And the Planck length represents the exact point where that consistency demands a hard stop. Below this scale, the concepts we use to navigate our world completely fall apart. The idea of distance loses its meaning. The arrow of time loses its direction. The reliable chain of cause and effect might just blur into an incomprehensible haze. Reality doesn't vanish, but it starts speaking a language we don't understand, a language that existed before our familiar concepts of space and time. This is precisely why every attempt to visualize what the Planck scale looks like is doomed to fail. Our imagination relies on geometry, on shapes and distances, but the Planck scale might exist in a state before geometry even emerges. It's a humbling realization. Human intuition evolved to help us survive in a world of meters and seconds, of throwing spears and finding shelter. It was never designed to grasp the deepest, most fundamental level of reality. Yet, here is one of humanity's quiet, unsung triumphs. Through the power of mathematics and observation, we can still reach far beyond the limits of our intuition. We may not be able to picture the Planck length, but we can understand its profound consequences. We can see how it acts as a stabilizing force in physics, how it elegantly resolves the terrifying infinities that would otherwise plague our theories, and how it protects reality from collapsing into self-contradiction. Without a smallest possible length, the quantum jitters of empty space would grow uncontrollably, tearing the universe apart. Without these built-in limits, gravity would crush everything into inescapable, infinitely dense singularities. The Planck length functions as a cosmic regulator, a silent, unwritten rule that keeps the entire universe coherent and knowable. In this light, it's not an obstacle blocking our path to knowledge. It's a safeguard. It's the very thing that ensures reality remains describable in the first place. This also forces us to reframe our idea of mystery. We often think of a mystery as a puzzle just waiting for us to find the missing piece and solve it. But what if some mysteries are structural? What if they exist not because of a lack of information, but because of the way reality is fundamentally built? The Planck length might be exactly that kind of mystery. Not a puzzle to be completed, but a boundary to be understood and respected. This doesn't mean scientific progress grinds to a halt. It means that progress might need to change direction. Instead of endlessly digging deeper into smaller and smaller scales, perhaps the future of physics lies in looking sideways. It might be about seeking new connections, identifying emergent patterns, and understanding how space-time, matter, and information all arise together as a unified whole. Probing ever smaller distances might become less important than figuring out the grand interconnected architecture of existence. From this perspective, the Planck length isn't the bottom floor of reality. It's more like a seam, a junction, where all our different descriptions of the universe meet and merge. Quantum mechanics, general relativity, information theory, thermodynamics, geometry. They all converge at this one unimaginably small point. This convergence strongly hints at a deeper unity. It suggests that at the most fundamental level, reality isn't made of separate, distinct pieces. It might be one single, intricate structure that we just happen to see from different perspectives. What we call space, time, matter, and energy could just be different shadows cast by a single, deeper framework that we have yet to fully comprehend. The Planck length marks the spot where all those shadows overlap and become one. This idea also changes how we think about knowledge itself. To know something doesn't always mean uncovering more and more granular detail. Sometimes, true understanding comes from recognizing why infinite detail cannot exist in the first place. The universe isn't hiding information from us. It is telling us, in its own quiet, subtle way, exactly how it works. It's showing us the rules of the game. As we move forward, we'll take one last step back to look at the full arc of this incredible idea. We'll trace its path from the smallest possible length to the largest questions of our existence. And we will ask a final, crucial question. Why does this discovery, now more than a century old, still matter so deeply to us today? Thank you for watching. And if you're enjoying this journey into the frontiers of science, make sure to subscribe for more. When we zoom out from the Planck length and look at the universe as a whole, something remarkable becomes clear. The smallest possible scale is not isolated. It quietly influences the largest questions humans have ever asked. Questions about our origin, our destiny, and our meaning. Physics often begins with measurement, but it doesn't end there. The deeper we go, the more physics starts to resemble philosophy, not because it becomes vague, but because it becomes foundational. The Planck length forces us to confront the very nature of explanation itself. Why does the universe have laws at all? Why are those laws stable? Why is reality structured rather than chaotic? At our everyday scales, these questions can feel abstract and distant, but at the Planck scale, they become unavoidable. If space-time, matter, and energy all emerge from something deeper, then that deeper structure isn't just another layer of smaller particles. It's the very framework that makes existence possible in the first place. This suggests that the universe isn't just a collection of objects, it's a process governed by fundamental constraints, and the Planck length is one of those constraints. It sets a limit on division. It sets a limit on precision. It sets a limit on what it even means to ask where and when. Now, you might think that limits like this weaken our explanations, but they actually strengthen them. A universe without limits would be completely unstable. Random fluctuations would grow without any bound. Geometry would collapse into chaos. Nothing lasting could ever form. It's precisely because there is a smallest scale that larger scales can exist. Stars can burn steadily for billions of years. Atoms can remain stable, forming the building blocks of everything we see. Life can evolve slowly and deliberately over eons. The beautiful calmness of the night sky depends entirely on the strictness of the universe's smallest rules. This connection between the extremes, the micro and the macro, is one of the deepest and most profound themes in all of physics. The smallest details shape the grandest structures. The quietest rules enable the loudest, most spectacular phenomena. Galaxies, spanning hundreds of thousands of light years, trace their origins back to tiny quantum fluctuations in the early universe. The cosmic structure we observe today, this vast web of clusters and voids, reflects a fundamental microscopic uncertainty. The sheer vastness of space emerges from a finite, granular resolution at its most basic level. This isn't just a poetic metaphor, it's a literal description of our reality. The universe is large because it is constrained. This idea also reframes our place within it all. We are often told that humans are insignificant because the universe is so mind-bogglingly large. But scale alone doesn't determine significance. Structure does. A universe that is capable of forming observers, creatures like us, who can look back and wonders already remarkable. A universe governed by precise, stable laws that allow for complexity is truly extraordinary. A universe with the smallest length, a feature that enables complexity to arise at all scales, is a concept that is rare in its conception and profound in its consequences. You exist because the universe has limits. Without a smallest length, reality would dissolve into a sea of instability. Without stable physical constants, time would have no rhythm, no forward direction. Without a deep coherence at the most fundamental level, nothing could persist long enough to matter. In this sense, the Planck length isn't some distant, abstract concept from a physics textbook. It's present in every single moment of your life. Every breath you take, every thought you have, every memory you form, all of it is supported by physical structures that depend on physics behaving predictably and consistently at the smallest possible scale. This perspective doesn't make life feel mechanical or deterministic. It makes it feel delicate. Our existence isn't guaranteed by chaos. It's sustained by an intricate and beautiful balance. The Planck length is a crucial part of that balance. It reminds us that reality is not infinitely malleable. It has a shape, it has a texture, it has boundaries. And it is within those boundaries that all the richness and complexity of life unfolds. So, as we've journeyed from the absolute smallest measurable scale to the widest horizons of our understanding, we see how the Planck length, this quiet and unassuming limit, stands as one of the most powerful and consequential ideas ever discovered. It's the silent foundation upon which everything else is built. Thank you so much for joining me on this exploration into the very fabric of reality. If you enjoyed this journey and want to dive deeper into the biggest ideas in science, make sure to like this video and subscribe to the channel. It really helps us continue making content like this. We'll see you in the next one. We began this journey by asking a simple question. What is the smallest possible distance in the universe? The answer, as we've discovered, takes us far beyond mere numbers and complex equations. It leads us to the very edge of what it means to describe reality itself. The Planck length isn't just an incredibly small measurement, it's foundational. It is the scale at which our familiar, everyday concepts of space and time begin to lose their authority. If we could zoom in to this level, geometry as we know it would dissolve. The act of measurement would fail. The language we use to describe the world would have to change. And yet, in this strange realm, nothing breaks. Reality doesn't just collapse into chaos. Instead, it transitions. The universe doesn't become a jumbled mess at its smallest scale. It becomes subtle, governed by a different kind of order. What might appear unstable from our macroscopic perspective is, in fact, highly structured from another. What seems like a fundamental limit actually becomes a rule, a condition that allows everything else to exist. This is a profound shift in thinking. The Planck length teaches us that limits are not always barriers. Sometimes they are the very conditions for possibility. It's because there is a smallest length that the fabric of space-time can remain coherent and stable. It's because there is a smallest unit of time, the Planck time, that the principle of cause and effect remains meaningful. And it's because there is a limit to how finely we can divide reality that structure can emerge and persist. From this single, foundational principle, everything else arises. The particles that make up matter, the fields that carry forces, the atoms that build molecules, the stars, the galaxies, and even life itself. Nothing in your direct experience is separate from this deepest layer of reality's structure. You are not just an observer looking at the universe from the outside. You are a living, breathing expression of it. The very same principles that govern the smallest possible scale are the ones that shape the largest patterns we see in the cosmos. The same quiet, unwritten rules that limit our ability to measure are the ones that enable meaning to exist in the first place. This realization doesn't shrink the universe or make it less wondrous. It deepens it. It adds a layer of intricate beauty. It reminds us that true understanding isn't always about reaching for infinity or wrestling with endless complexity. Sometimes, it's about recognizing the profound coherence that underlies everything. It's about seeing how an elegant simplicity can give rise to an incredible richness and diversity. The Planck length is one of those rare scientific ideas that grows more powerful and more meaningful the longer you consider it. It starts its life as a technical constant in a physicist's equation, but it ends as a philosophical boundary, a line between the knowable and the unknowable, the divisible and the fundamental. It tells us that reality is not an infinitely smooth, continuous expanse. It's not infinitely divisible. It has a texture. It has a rhythm. It has a resolution, like a digital image. And it is within that finite resolution that everything we see, everything we are, everything we can ever know unfolds. So, as you go about your day, let these ideas settle. Take a moment to remember that every second of your existence, every thought you have, Every breath you take occurs within a universe governed by a quiet, unspoken precision. The smallest, most fundamental rules are the ones holding the largest and most magnificent structures in place. This isn't something to fear or feel small about. It is something to appreciate, to marvel at. The universe isn't cold and indifferent. It is consistent, and that deep, unwavering consistency is the very thing that allows anything to be at all. Thank you for taking this slow, contemplative journey with me down to the smallest scale of reality. If this exploration brought you a sense of calm or sparked a new curiosity, you are always welcome to return. The universe will still be here, quiet, structured, and patient. Thanks for watching.